Welcome back to the Deep Dive. Our mission here, as always, is to take those dense stacks of sources, all that research, technical docs, and boil it down into something you can actually use. Today, we're looking up, way up, and this is the key part with a big constraint, portability. So this deep dive is really for you, the urban astronomer, when looking out at that frustratingly bright, light-polluted city sky thinking, well, deep space astrophotography, that's just not for me. Not unless I have a dark sky sight and like a truck full of gear. If you've got physical limits, maybe not much storage space, or honestly, just the thought of lugging some massive setup around completely puts you off. Well, this is your guide. We're talking about imaging deep space objects, maybe even tonight, without, throwing your back out.
That's exactly it. That's the core mission here. We're exploring what we call astrophotography on the go. And the goal is to show you that getting really high-quality deep space images, it's totally possible. You can do it with kits that are genuinely lightweight, genuinely portable. The whole philosophy, it kind of flips the traditional method on its head. We're ditching those classic, hour-long single exposures. Instead, we're taking maybe hundreds of really short exposures. Think 15 seconds, maybe 30 seconds max. And then we use some pretty clever digital stacking techniques to build up that final photograph.
Okay, but before we jump into the cameras and telescopes, we really need to define portable. Because, the astronomy world, movable and portable can mean wildly different things, right?
Oh, absolutely. Yeah, we need a clear line in the sand here. There's a sort of portability philosophy that's pretty common in this part of the community. And the core rule is basically this. If you can't carry your entire kit, and that includes your observing chair, everything, in one single trip from wherever you store it to where you set up, well, then it might be movable, sure. But it's not truly lightweight or portable in the sense we mean. One trip, that's the test.
One trip, I like that. It's practical.
It has to be. And this definition, it's really vital because, statistically speaking, most people who might want to try this, they live where this approach is pretty much required. We're talking roughly 80% of people in developed places like the US, the UK, they live in urban or suburban settings. Light pollution is just a fact of life. So for those millions, the old school requirement of a huge, heavy, maybe even permanent setup, it just makes the hobby impossible. It's a non-starter. A light, fast kit, though, that's what lets someone go from just being an armchair astronomer, reading about the Messier objects to actually getting out there and capturing them.
Yeah, that one trip rule, I think that's a perfect constraint. It really respects the reality of maybe you live in a small apartment or you just don't have hours and hours to set up. If it takes 3 hours just to get going, you're probably never going to do it on a random Tuesday night, are you? You need it to be quick, minimal hassle. #2, the technological revolutions that enabled portability. Okay, let's unpack the mechanics here. Because the idea that you can take, say, a 30-second snapshot, stack it with a bunch of others, and somehow get the equivalent of an hours-long exposure, it almost sounds like you're cheating physics a little bit. What actually changed? What were the big technological shifts that made this short exposure approach even possible, that let us get away from the really demanding requirements of the old film days?
Yeah, it really does seem counterintuitive at first, but there were basically two big revolutions happening more or less at the same time that just completely transformed amateur astrophotography, took it from this massive, expensive commitment into something much more accessible.
Okay, let's start with the cameras themselves. What happened there?
Right, so that was the digital imaging revolution. Specifically, the rise of the DSLR, the digital single-lens reflex camera. Before, say, the early 2000s, digital cameras just weren't really sensitive enough. They had too much internal noise, electronic noise, to capture those really faint, deep space objects, the DSOs, very well. But then the sensors got better, prices came down, and suddenly DSLRs had enough resolution, enough sensitivity. And the key thing they enabled wasn't just taking the picture digitally, it was the ability to digitally combine those pictures, to stack, hundreds of short exposures into one final image that pulls out all that faint detail.
And the practical impact of that, it's huge, isn't it? I remember hearing stories from older astrophotographers, the absolute dread of spending 4 hours on a single perfect shot on film.
Oh, yeah.
Only for a satellite to streak right through the middle, or maybe just a tiny gust of wind nudges the scope. Boom, the whole night's work just ruined.
Exactly. That whole disaster scenario, it's pretty much ancient history now with digital. If one of your 30-second frames gets ruined by a passing airplane, you just toss that one frame out. Your total integrated exposure time barely even notices it. It's a huge weight off your mind. But maybe even more fundamentally, the sensitivity of modern digital sensors and how low their internal noise is, especially dedicated astro cameras, or even just decent DSLRs, that's now good enough. Good enough to capture the incredibly faint signal from many DSOs using really short exposures, like we said, 30 seconds, sometimes even less. And you can still get what we call usable signal-to-noise ratio, the SNR. Even with a relatively, slow telescope, that faint signal is actually there above the noise floor, even in that short time.
Okay, so that's the foundation. You can actually capture something usable really quickly, and then you let the computer do the heavy lifting later, adding it all up. Was the second revolution, the one about how the cameras are actually held and pointed at the sky.
Ah, right. That was the computerized mount revolution. Everyone just calls it GOTO technology. It really started taking off in the early 90s, got better and cheaper really fast. These GOTO mounts, they automatically find objects for you, center them in the eyepiece or camera, and then track them as the Earth rotates. Initially, they were seriously expensive, like prohibitively so for most amateurs, but the accuracy just kept improving and the prices dropped dramatically. Suddenly, they were within reach for serious hobbyists.
And this is where that debate always flares up in the astronomy clubs, right? The purists versus the pragmatists.
Oh, absolutely. It still does to some extent. You have the traditionalists who argue quite passionately sometimes that GOTO mounts take away the need to actually learn the night sky. They'll say, newcomers should learn the constellations. They should master star hopping with finder charts, manually find those faint fuzzies. Relying on a computer means you never really know the sky. And look, I get that sentiment. I really do. But the pragmatists, they come back with, well, the main goal is to observe the object, right? Not necessarily the treasure hunt to find it. Plus, and this is crucial for our topic, GOTO is often almost essential in light-polluted urban skies. Why? Because many of those faint guide stars you'd use for traditional star hopping, you just can't see them from the city. So light pollution basically makes the traditional approach impossible sometimes. GOTO just lets you bypass that problem, find your target quickly, and start imaging.
So GOTO actually helps the city dweller even before the first picture is snapped.
Okay.
And mechanically, how did this change things? How did GOTO relax the really strict requirements for the physical mount itself?
It changed the game completely in terms of required stability. The old way, the film way, you needed a massive mount, usually a German equatorial mount, a gem. We're talking 80, maybe 100 pounds of metal. And it had to be meticulously aligned with the Earth's axis, polar aligned, and engineered to be incredibly rigid. Absolutely vibration-free for minutes, maybe even hours during that single long exposure. But with this digital stacking approach, that extreme requirement just evaporates. The mount doesn't need to provide hours of flawless, rock-solid stability anymore. It only needs to give you sort of short periods of stability while it's tracking the object. 30 seconds, maybe a bit less. That's it. And that level of tracking accuracy, that short-term stability, it's well within the capabilities of many much cheaper, much lighter GOTO mounts that might weigh less than 10 pounds.
Okay, so we're moving from the theory, the short exposures, to the actual stuff we can carry in that single trip. If we can't or won't haul out a giant GM, what are the options for lightweight mounts? And more importantly, what are the limitations? What trade-offs do those lighter choices force on us?
Right. This brings us straight back to the type of mount, because the fundamental limitation of most truly portable setups is the difference between how equatorial mounts track and how alt-azimuth mounts track.
Let's just quickly recap how a GM works, the big heavy ones.
Sure. A German equatorial mount, a GEM, is designed to be aligned very precisely with the celestial pole, Polaris, in the northern hemisphere. Once you've done that alignment, it only needs to rotate around one axis, the right ascension axis, at a constant speed, 15 degrees per hour, to perfectly counteract the Earth's rotation. Because it's moving smoothly around just one axis that mirrors the sky's motion, the stars in your camera stay perfectly still, pinpoints. This allows for those minutes-long unguided exposures, assuming your alignment is spot on.
Okay, now the alt-az mounts, the kind you usually find on lighter, more portable GOTO scopes.
Right. The alt-azimuth mount works differently. It tracks objects by making constant, tiny corrections in both altitude, up, down, and azimuth, left, right, simultaneously. And because it's trying to follow the curved path of a star across the sky, using these two straight-line movements relative to the ground, it introduces a really problematic geometric effect called field rotation.
Field rotation. Okay, so rotation. That sounds bad for photos. Even if it's subtle, I guess that means the stars aren't pinpoints anymore. They start to trail.
Exactly.
Yeah.
Instead of nice round stars, the stars, especially those further away from the very center of your image, start to appear slightly elongated. They look like tiny little arcs or streaks rotating around the center point of the frame. It ruins that deep sky look you're going for.
Can you help visualize why moving an alt-az causes this? Why does up, down, and left-right movement make the view rotate?
Okay, think about it like this. Imagine you're standing right at the North Pole. Everything in the sky just pivots perfectly around a point directly above your head, right? That's kind of what a perfectly aligned GM does. It rotates on one axis that matches that celestial rotation. An alt-azimuth, though, it's stuck on the ground. It's trying to mimic that smooth, curved celestial motion by using two straight movements, up, down, left, right. Imagine trying to trace a perfect circle on a piece of paper by only moving two straight rulers, one horizontally and one vertically. You'd have to make lots of tiny adjustments, and the resulting path wouldn't be perfectly smooth. Those tiny adjustments, that's kind of like the alt-azimuth tracking, and it's those little discrepancies that manifest as the field appearing to rotate over time.
Okay, I think I get the concept. And where's this rotation effect worst? Does it depend on where you're pointing the telescope?
Oh, absolutely. It depends hugely on where the object is in the sky relative to your location. The effect is worst, meaning the rotation is fastest when you're pointing straight overhead towards the zenith. It gets progressively less severe as you point closer to the horizon or closer to the celestial pole, like near Polaris if you're in the north. The math behind it is a bit involved, but the practical result is stark. Say you're observing from a typical mid-latitude location, maybe 40 degrees north, if you target an object that's nearly straight up near 90 degrees altitude. Field rotation basically limits your usable exposure time to, well, effectively 0 seconds before stars start trailing noticeably. You just can't take any meaningful exposure up there with an alt-azimuth for deep sky. But conversely, if you look at something much lower in the sky, say down at only 10 degrees altitude and maybe due north or south, 0 degrees azimuth, the rotation effect is minimized way down there. In that specific case, you might be able to get away with an exposure up to, say, 39 seconds before the trailing becomes unacceptable. So this reality, this field rotation problem, is the absolute main reason why deep sky astrophotography with portable alt-azimuths is strictly limited to those very short exposures we talked about. Usually around 30 seconds is the practical maximum. Any longer, and even the best stacking software will struggle to fix the badly trailed stars.
Okay, so the mount choice, the portable alt-azimuth, forces this 30-second cap on us because of field rotation. That means we absolutely have to compensate by grabbing as much light as possible through the telescope in that short time. Which brings us straight to the telescope's optics, and specifically the focal ratio, or fratio.
Correct. Speed, optical speed, becomes paramount. The fratio number tells you how bright the image is formed at the camera sensor. A lower fratio number means a faster telescope, a brighter image, which means you need less exposure time to capture the same amount of light, the same signal from your faint target. We generally categorize scopes like this. Fast scopes are typically f6 or lower. Medium speed is maybe f6 up to about f8. And anything higher than f8, we consider that pretty slow for imaging purposes.
And here's the rub. A lot of really popular, quite portable telescopes, things like the Schmidt-Cassegrains, SCTs, or the Maksutov-Cassegrains, they tend to fall into that slow category, don't they?
They absolutely do. Most SCTs you buy off the shelf are f10. Maksutovs can be even slower, often f12, sometimes even f15. They give great high-power views, but they are inherently slow optically. So if you try to take a 30-second exposure through an f12 Mac, chances are you'll capture, well, mostly just noise. Maybe the very brightest stars, but certainly no faint nebula. This means if you want to use a portable SCO or Mac for this short exposure technique, getting a focal reducer isn't just a nice-to-have accessory. It's pretty much essential, non-negotiable.
Explain what that does, the focal reducer. How does it speed things up, and what kind of gain are we talking about?
Right. A focal reducer is basically an extra lens assembly. You typically screw it onto the back of the telescope tube just before your camera. What it does is shorten the effective focal length of the telescope. Shorter focal length at the same aperture means a lower fratio. So for a typical f10 SCT, the standard accessory is a 0.63x focal reducer. You put that on, and it transforms the telescope's effective speed from f10 down to f6.3.
Okay, f10 down to f6.3, that sounds significant.
It's huge. Mathematically, brightness increases with the square of the change in fratio. So going from f10 to f6.3 makes the image, 10.6.32, equals 2.5 times brighter for the same exposure time. Or put another way, it improves your signal-to-noise ratio by a factor of the square root of that, which is about 1.59 for the same exposure length. You're basically collecting light almost 60% faster just by adding that one little optical component. It makes a massive difference for short exposures.
Okay, let's pivot to some specific hardware examples that might actually fit our one-trip rule.
Yeah.
What are some good options for the telescope tube itself, keeping portability and speed in mind?
Well, short tube achromatic refractors are always really tempting. You know those little scopes like an 80mm f5? They're super fast, very lightweight, often under 5 pounds. Seems perfect, right? The main drawback, though, with simple achromatic refractors is chromatic aberration. Because they use a simple two-element lens, they don't bring all the colors of light, especially blue, to the exact same focus point. In photos, this shows up as annoying blue or purplish fringes or halos around brighter stars. It can kind of ruin the aesthetic.
Right, those blue halos. So if you want to avoid that, but you don't want the cost and, frankly, the extra weight of a premium apochromatic refractor, an APO with 3 or more lens elements, what's the alternative for sharp, color fringe-free images in a portable package?
That's where those small SCTs we mentioned really come into their own, provided you use that focal reducer. Take a Celestron C5, for example. That's a 5-inch, 125mm aperture SCT. The tube itself only weighs about 6 pounds. Very manageable. You add the 0.63x reducer, now it's operating at a very respectable f6.3. And because it uses mirrors, SCTs are naturally free of chromatic aberrations. You get sharp stars, great contrast, no color fringing. It's a fantastic, high-quality portable option.
And one last practical point you mentioned earlier about the mounts themselves, those common GOTO alt-and-as mounts, like the Skywatcher, Synscan AZ, or similar ones. You said they're often tougher than they look regarding how much weight they can carry.
Yeah, they really are surprisingly robust for their size and weight. These lightweight GOTO Alt-as mounts, their official payload ratings are often quite conservative. We see this all the time in the community. People routinely load them up maybe 50% over their stated capacity, and they handle it just fine for visual use and especially for short exposure photography where perfect tracking isn't needed for minutes on end. So say a mount is officially rated for 8 pounds. You can probably push that to 10, maybe even 12 pounds without major issues for this kind of work. And that extra margin, it really opens up your options. It means you can comfortably put that C5 SCT on there, or maybe even a slightly heavier short tube refractor. It gives you much more flexibility in your optical choice than you might think, all while staying genuinely portable.
All right. This is where, for me anyway, it gets really interesting and maybe a bit mind-bending. We're relying on taking dozens, maybe hundreds of these quick 15 or 30-second snapshots. They look noisy, they look faint on their own. How does combining them magically turn into the equivalent of a really long, deep exposure? It feels like there should be a catch. How does this noise reduction actually work?
It does feel a bit like magic, but it boils down to the mathematics of how signal adds up versus how noise adds up. But first, let's talk about just capturing one of those short frames. Because they are so short, like you said, they're fundamentally underexposed. The faint light from your nebula or galaxy is mostly buried way down in the electronic noise of the camera sensor right from the start.
And the way we try to compensate for that, to pull that faint signal out, is by cranking up the camera's ISO setting.
Right.
But that sounds like a delicate balancing act itself.
Oh, it's a very tight balancing act. If you push the ISO too high, yes, you amplify those faint details, which sounds good. That's the goal. However, aggressively boosting the ISO also effectively lowers the camera's white point, the level at which things saturate to pure white. The result is that anything bright in your image, the cores of stars, the bright nucleus of a galaxy, they tend to blow out or bloom really easily. They lose all their color, all their detail, all their contrast, just become white blobs.
Okay, so that's the risk of going too high on ISO. What about setting it too low? Trying to be conservative.
Well, if the ISO is too low, your image will be very dark, obviously. The faint stuff might not register at all. But worse, the darker areas will be heavily affected by read noise. That's the baseline electronic noise from just reading out the sensor. It can show up as ugly patterns like banding in the dark background of your final stacked image. But perhaps the most critical problem with setting the ISO too low is that the stars themselves might end up being too dim. Remember, the stacking software programs like Deep Sky Stacker, they need to see stars clearly in each frame to know how to align it perfectly with the others. You generally need like a minimum of 15, maybe 20 well-defined stars detected in each and every frame for the software to lock on and do its job properly. If your stars are just too faint and mushy because the ISO is too low, the computer literally can't find enough reference points. The stacking fails, and your whole night of capturing frames could be wasted. So the goal isn't necessarily to get a single frame that looks beautiful on the camera screen. It's to get a frame that's just bright enough for the software to work with.
That's a key distinction. The individual frame is for the machine's benefit, not really for the human eye yet. Okay. Now, Let's dive into the math that makes stacking these noisy frames worthwhile. Explain the core science here. How does stacking actually improve the image and tackle that noise?
Right. The absolute central principle you have to grasp is this. Stacking primarily increases the signal-to-noise ratio by reducing the noise, not by magically increasing the signal level beyond what's in a single frame. When you stack, say, 100 frames, the actual brightness level of your target nebula in the final image is essentially the same as its brightness in one of those single frames, but the noise level is dramatically lower. Now, here's the crucial mathematical difference. The signal you want the light from the nebula, it accumulates linearly with exposure time. Double the time, you get double the signal photons hitting the sensor. Simple. However, the random noise, things like thermal noise, read noise, shot noise, it doesn't add up as fast. Its contribution only increases as the square root of the signal, or effectively the square root of the exposure time.
Okay, hold on. Signal goes up linearly with time. Noise only goes up with the square root of time. So the signal always climbs faster than the noise does over time.
Exactly. And that's why longer individual exposures inherently have a better SNR. But here's how stacking leverages that. When you stack multiple frames, the software aligns them perfectly based on the stars. So the faint signal from your nebula in each frame lines up precisely and adds together constructively, essentially linearly. But the noise in each frame, it's random, it's different in every shot. So when you average or median combine those frames, the random noise tends to cancel itself out. It doesn't add up constructively. Mathematically, the noise level in the final stacked image is reduced by the square root of the number of frames you stack.
Okay, let's make it concrete. Walk us through that comparison from the sources, the one using a total imaging time of 75 minutes, which is 4,500 seconds, comparing two different approaches to get there.
Right. Let's imagine two hypothetical imaging sessions, both totaling 75 minutes. Session A is maybe closer to a traditional approach, but still using relatively short exposures, let's say 100 frames, and each one is 45 seconds long. 100 by 45 equals 4,500 seconds. Session B is our true astrophotography on the go method, 300 frames, and each one is only 15 seconds long. 300 by 15 equals 4,500 seconds, same total time. Now let's think about the signal-to-noise ratio, the SNR, of a single frame in each session. The 45-second frame, session A, will naturally have the better SNR than the 15-second frame, session B, because it captured more signal relative to noise in that longer time. Let's just assign some relative values. Say the SNR of 115's frame is 1 and the SNR of 145's frame is 1.7. Okay, now the magic of stacking. How much does the noise get reduced in each case? For stack A, we have 100 frames. The noise reduction factor is the square root of 100, which is 10. For stack B, we have 300 frames. The noise reduction factor is the square root of 300, which is about 17.3. So when you calculate the final SNR of the stacked image, which is basically the single frame SNR multiplied by the noise reduction factor, or square root of n, stack A 1.7, single frame SNR 10 squared 100, SNR 17.3, square root of 300, stacking result. They have virtually the same final signal to noise ratio. Both stacks end up with an SNR of around 17.
Wow, okay, that is powerful. So the math clearly shows that purely from a noise perspective, you can absolutely trade longer individual exposures for just taking a whole lot more really short ones, as long as the grand total time you spend imaging is the same. But that begs a huge question then. If the noise ends up the same, why did anyone ever bother with those incredibly demanding 20 or 30-minute single exposures on film? Why not just take, like, thousands of 1-second exposures? Where does this logic break down?
That is the crucial question, and it brings us right back to the trade-offs involved. You're right, the final SNR based on noise reduction might be the same in our example. However, the image produced from the stack of longer individual frames, stack A in our example, will still look different. It will be inherently brighter, have better initial contrast, better definition before you start stretching it and processing. Remember, we said the signal in a 45-second frame was maybe 16 times stronger than the signal in a 15-second frame in one analysis. That stronger initial signal makes the subsequent processing steps easier and often yields a smoother result. But more importantly, there's a floor to how short you can make the exposures before other problems dominate. If you drop down to, say, 1 or 2-second exposures, you run smack into two major issues: read noise dominance and quantization error.
Okay, what are those?
Read noise, as we mentioned, is that constant electronic noise floor from the camera reading the sensor. It happens every single time you take a picture, regardless of how long the shutter was open. In a decent 30-second exposure, the actual light signal you're capturing from your target, even if it's faint, is usually significantly stronger than this baseline read noise. The signal wins. But in a tiny 1-second exposure, the incoming light signal is incredibly weak. So weak that it might be completely swamped, completely buried by the camera's own read noise. The noise wins, and you effectively capture nothing useful. The other issue is the camera's analog to digital converter, the ADC. This chip converts the analog light signal into digital numbers. It has discrete steps. If you only expose for a fraction of a second, the very faintest parts of the nebula might generate such a weak signal that they fall below the smallest step the ADC can even measure. It's like the camera just doesn't see them at all. That's quantization error. You're literally losing the dimmest data because the exposure was too short for it to register digitally. So while 15 to 30 seconds seems to be a sweet spot long enough to get above the read noise, short enough to work with portable mounts, you really can't just drop the exposure time down indefinitely. There's a lower limit.
That makes perfect sense. Okay, so we need those 15, 30-second exposures. We need lots of them. But taking hundreds of short, noisy exposures means we're also capturing hundreds of instances of the camera's own flaws, hot pixels, dust specks, uneven illumination. We can't just stack those raw light frames directly, can we? This sounds like where calibration frames come in. Darks, flats, bias. Okay, this part always sounds like extra homework. Can you quickly define what these three types of frames are and maybe tell us which specific problem each one is designed to fix?
Haha, it definitely feels like homework, but it's absolutely non-negotiable homework if you want good results, especially with the short exposure method. These calibration frames are designed to map out and let you remove the systematic errors that are inherent to your specific camera and telescope setup. Okay, first step. Dark frames. How do you take them? You completely cover the front of your telescope or camera lens so absolutely no light gets in. Then you take a series of exposures that are the exact same duration, for example, 15 seconds, and ideally at the same temperature as your actual light frames of the nebula. What do darks fix? They primarily combat dark noise and thermal noise. This is noise generated just by the sensor itself existing and heating up slightly during the exposure. It creates fixed hot pixels that are always bright and a general random static, especially noticeable in the dark background areas. By subtracting a master dark frame made by averaging many individual darks, you're essentially telling the software, okay, ignore these specific bright pixels, they're just sensor defects, not actual stars, and subtract this general thermal glow.
Got it. Darks handle the heat noise. What about bias frames?
Bias frames are usually the quickest ones to capture. You take these again with the lens cap on, absolutely no light. But this time you use the absolute shortest possible exposure time your camera can manage, often 14,000th or 18,000th of a second. What do bias frames fix? They capture the read noise pattern we talked about earlier. This is the inherent electronic noise generated purely by the process of reading out the data from the sensor chip through the camera circuitry. This pattern is present in every single image you take, including your lights, darks, and flats. By creating and subtracting a master bias frame, you map out and remove this constant electronic fingerprint, this baseline noise pattern. And finally, flat frames. These are a bit different. To take flats, you need to point your telescope at a perfectly evenly illuminated, featureless surface. Common methods include using a dedicated flat panel light box, pointing at a plain white t-shirt stretched over the scope opening, or even carefully pointing at the blank twilight sky just after sunset or before sunrise. The key is uniform illumination. You then take exposures that are just long enough so the image histogram looks about half full, not too dark, not blown out white. What do flats fix? They tackle two main things: vignetting and dust motes. Vignetting is that natural darkening you often see towards the edges and corners of an image, just due to the telescope's optical geometry. Dust motes are annoying little specks of dust that might be lurking on your camera sensor, or maybe on your focal reducer lens. They show up in your images as dark, often donut-shaped shadows. By dividing your light frames by a master flat frame, the software corrects for both these issues. It brightens the corners to match the center, effectively removing the vignette, and it cancels out those pesky dust donuts, leaving you with a clean, evenly illuminated background.
Okay, that clarifies things a lot. Darks for thermal noise, bias for read noise, flats for dust and uneven lighting. If we're aiming to take, say, 100 to maybe even 400 of those light frames for a good final image, how many of these calibration frames do we realistically need to take?
It's the same principle as with the light frames. Really, the more calibration frames you stack together to create your master dark, bias, and flat, the lower the noise within those master calibration frames themselves. Ideally, if you took 100 light frames, you'd want to take 100 darks, 100 flats, and 100 bias frames to ensure you're subtracting a very clean, low-noise calibration signal. You don't want your calibration frames to actually add noise back into your final image. However, for practical purposes, especially with short exposure work where noise is already averaged down significantly, taking around 49 frames of each type, darks, flats, bias is generally considered a good minimum acceptable number. Stacking 49 frames reduces the noise in the master calibration frame significantly enough that it won't unduly contaminate your final result.
49? That's still a fair number, but maybe more manageable than hundreds. So the overall logistics for a good imaging session using this method are pretty intense there. We're talking maybe 2 to 3 hours of actual imaging time just collecting the light frames. Plus, you need time before or after to capture maybe 50 darks, 50 flats, 50 bias frames. And you mentioned something about a pause between light frames too.
Yeah, that's right. Most DSLRs and even dedicated astro cameras need a few seconds. Typically around 5 seconds is common between each exposure just to process the image internally and save it to the memory card before it can start the next one. So yeah, when you add it all up, hundreds of light frames plus the pauses plus capturing all 3 sets of calibration frames, it's definitely a volume game. You end up generating a lot of data files in one night. #DSTagV image processing and battling light pollution.
Okay, so the imaging session is done. We've got this potentially huge pile of digital files sitting on a computer, hundreds of calibrated light frames, plus our master darks, flats, and biases. Now what? We need software to actually perform the magic of combining them all. And then, once they're stacked, we still have to deal with that elephant in the room for many of us, the unavoidable gray, hazy signature of the urban sky baked into our image.
Right. The first major step is the stacking pipeline itself. And for the vast majority of amateur astrophotographers, especially those starting out, the go-to software for this is Deep Sky Stacker, or DSS. It's incredibly popular, partly because it's free, but also because it's just really, really capable. It handles the whole process, registering, aligning the stars, calibrating each light frame, using your master darks, flats, and bias, and then stacking them all together into that final deep image.
Okay, DSS. Are there any specific settings within DSS that are particularly important for us, given that we're dealing with this huge volume of very short, potentially quite noisy exposures?
Yes, absolutely. For these high frame counts, probably the single most critical setting to get right in DSS is the stacking mode. You'll usually want to select the median mode.
Median, not average. Why median?
Good question. Standard stacking often defaults to using an average calculation, which sounds fine, but think about what happens if one of your 300 frames happens to have a bright satellite or an airplane trail streaking through it. If you use average stacking, that bright trail contributes to the overall average pixel value along its path, and you'll end up with a faint, ghostly remnant of that trail visible in your final stacked image. The median mode, however, works differently. For each pixel location in the final image, it looks at the value of that pixel across all your input frames, say all 300 values, sorts them, and then picks the middle value, the median, not the average. This makes median stacking incredibly powerful at rejecting outliers. That bright satellite trail. It's an outlier value in maybe 1 or 2 frames out of 300. It's nowhere near the median value for those pixels, so it gets completely ignored in the calculation. Same goes for random cosmic ray hits or even minor tracking errors or hot pixels that weren't perfectly removed by the darks. Median just throws out the weird data. It's perfect for cleaning up stacks made from lots of short frames. Oh, and one other thing to watch in DSS, especially if you're using a DSLR, is how it handles the initial raw file development. Sometimes the default settings aren't quite right for astro images. For example, with Canon EOS cameras, it's very common that you need to go into the raw fit settings in DSS and manually adjust the color balance before stacking. A typical tweak is setting the red scale multiplier to maybe 1.25 and the blue scale to 1.00. This corrects the camera's built-in white balance bias and helps ensure your final stacked image has more accurate, natural-looking star colors. You might also want to set the white balance setting itself to auto or camera white balance within DSS.
Right, got to get the colors right from the start. Okay, so DSS works its magic using median stacking and spits out a final image file. But even though we might have stacked, say, 75 minutes worth of total exposure time, that resulting file, it usually looks incredibly dark, doesn't it? The nebula or galaxy is often barely visible. This is where we get into the complex, maybe even artistic phase known as stretching the image.
Exactly. This is the crucial and often tricky step, the challenge of stretching. Your freshly stacked image file from DSS is typically saved as a 16-bit file. That means it contains a huge potential range of brightness levels, 65,536 levels to be precise, from pure black, 0, to pure white, 65535. However, all the faint, interesting light from your deep sky object, it's all compressed down into just the very, very darkest levels of that enormous range, right down near zero. The vast majority of the image data range is just representing slightly different shades of dark sky background, so we have to stretch the image, which basically means applying a carefully controlled nonlinear brightness curve adjustment. We want to dramatically brighten those faint signal levels where the nebula lives, while trying not to blow out the brighter stars or make the background sky look too bright or noisy.
Okay, stretching to bring out the faint stuff. You mentioned a potential pitfall here related to the bit depth. You said the stack file is 16-bit. What happens if someone tries to do this stretching using, say, a basic photo editor that only works in 8-bit? You mentioned something called banding. How can I explain that to listeners? Is it like lakes just running out of shades of gray?
That's a pretty good way to think about it, yeah, but the effect is often more jarring than just looking coarse. The core problem is exactly that bit depth difference. Your 16-bit stacked file, remember, has 65,536 possible brightness steps. Think of it like an incredibly smooth, continuous ramp of tones from black to white. Now, an 8-bit image format, which is what most standard JPEGs use and what many simpler photo editing programs are limited to internally, it only allows for 256 distinct brightness levels. That's it. So when you try to take that super smooth 16-bit gradient and aggressively stretch it, forcing it to fit into only 256 available slots using 8-bit software, the software has no choice but to make harsh decisions. It has to essentially round off huge ranges of those original 65,536 levels and assign them all to just one of the 256 available 8-bit levels. Where your original 16-bit data had subtle, smooth transitions like the gentle fade of nebulosity, the 8-bit stretched version develops these visible steps or shelves where the brightness jumps abruptly from one level to the next. That's the banding artifact you see. It looks like contour lines on a map, and it means you've physically thrown away image data and lost all the fine, smooth detail in those faint regions.
Okay.
So using an 8-bit program to stretch a 16-bit astro image literally damages the data, which means specialized software isn't just recommended, it's basically mandatory if you want to preserve the integrity of all that data you worked so hard to capture.
Absolutely mandatory. You need to perform the critical stretching steps using software that can work natively and maintain precision in 16-bit or even 32-bit floating point calculations. This typically means using either high-end general-purpose image editors that support high bit depths properly, like the full version of Adobe Photoshop CC, or more commonly in the astro community, using dedicated astronomical image processing software. The big name there is PixInsight, which is incredibly powerful but also known for having a very steep learning curve and a significant cost. But there are also more affordable and often easier to learn options like StarTools, which is specifically designed from the ground up to handle the unique challenges of processing deep sky images, especially ones that start out very dark and need aggressive stretching, like the results from our short exposure stacking method. Okay, specialized software is a must. Now let's finally tackle that bright city sky issue, light pollution. It blankets everything in this sort of dull gray-orange haze. How do we fight back against that when we're doing portable astrophotography right from the urban jungle?
Yeah, it's the perennial challenge for city-based imagers. And the context here is pretty stark. Typical urban sky glow often measures somewhere between 17th and 19th magnitude per square arcsecond in terms of brightness. To put that in perspective, a sky illuminated by a full moon is typically around 18th magnitude per square arcsecond. So imaging from the city can literally be like trying to see faint fuzzies during a full moon every single night. It drastically reduces the contrast between your target and the background sky. The most effective weapon we have in our portable arsenal against this is the use of light pollution reduction filters, or LPRFs, sometimes called nebula filters.
Filters. Okay, but filters inherently block some light, don't they?
Yeah.
How does adding a filter help when we're already struggling to capture faint signals with short exposures? Doesn't it just make things dimmer?
That's the common concern. But these filters are cleverly designed. They aren't just neutral density filters that dim everything equally. LPRFs are designed to be highly selective. They contain special optical coatings engineered to block very specific, narrow wavelengths of light, namely the wavelengths emitted by common types of artificial street lighting. Think the characteristic yellow glow of high-pressure sodium vapor lamps or the greenish tint of older mercury vapor lamps. Some newer broadband filters even target specific peaks in the spectrum of white LED streetlights. Crucially, these filters are designed to pass most of the light coming from the astronomical objects we want to image, especially emission nebulae, which glow brightly at specific wavelengths like hydrogen alpha, red, and oxygen the third, blue-green. So They significantly cut down the unwanted background sky glow noise while letting most of the desired signal from the nebula or galaxy pass through relatively untouched.
Okay, so they selectively kill the bad light. What kind of real-world impact can this have? Does it make a noticeable difference in the final image contrast?
Oh, a huge difference. The quantitative impact can be really dramatic. The key is that the reduction in the overwhelming sky glow noise is far, far greater than the slight reduction in the brightness of the actual target object. Let's use a hypothetical example from the sources. Imagine you're imaging a nebula from the city without a filter. Maybe the faint outer regions of the nebula only exhibit, say, 16% average contrast against the bright sky background in your raw data. It's barely distinguishable. Now, you add a good broadband LPRF filter, something like an Optolong L Pro or similar. By cutting out maybe 90% of that artificial sky glow while still passing maybe 90% of the nebula's light, the contrast jumps dramatically. In the sources example, that average contrast might leap up to something like 143%. Suddenly, those faint structures that were lost in the mush are clearly visible. You can capture features with much greater definition, much better contrast, even when you're shooting right from your light-polluted backyard or a nearby city park. For urban imagers using this short exposure technique, a good LPRF is often the single most impactful piece of gear they can add. So, while capturing those faint, deep space objects, the nebulae and galaxies, is often the main goal for people using this portable, short exposure technique, it's worth mentioning that these lightweight tracking kits are actually perfectly suited for a couple other related types of astrophotography as well.
Oh yeah, like what else can you do with a small tracking mount in a DSLR?
Well, one really popular technique is piggyback photography. This is super straightforward. Instead of attaching your camera directly to the telescope's focuser, you just mount the camera with its own normal camera lens attached onto the top of the telescope tube, or maybe directly onto the tracking mount itself. The mount does the job of tracking the sky's rotation, keeping the stars sharp, but the picture is taken through your standard camera lens, maybe a wide-angle lens, or a short telephoto. This is absolutely ideal for capturing really large, deep sky objects, or huge swaths of the Milky Way that would be far too big to ever fit into the narrow field of view you get when shooting through the telescope itself. Think targets like the enormous Rosette Nebula, or the entire Andromeda Galaxy region, or those incredibly dense star fields down in Sagittarius near the core of our galaxy.
Ah, right, so you're using the mount just for the tracking, but the optics of the camera lens. The difference in the field of view must be huge compared to looking through the scope.
Oh, it's massive. A typical telescope setup for DSO imaging might only capture a patch of sky that's maybe 1 or 2 degrees across. Tiny. But if you piggyback your DSLR with, say, a standard 50mm lens, you're capturing maybe 40 degrees of sky. Put a 20mm wide-angle lens on there, and suddenly you're capturing a field that's nearly 60 degrees wide along its long axis. This flexibility lets you frame these really expansive celestial scenes, maybe showing constellations interacting with parts of the Milky Way, in a way that's just impossible with the high magnification view through the telescope.
Okay, piggybacking for wide fields.
Yeah.
What else? You mentioned another category.
Yeah. The other related area is nightscape photography. This one often doesn't even strictly require the tracking mount, although sometimes short-tracked exposures can help. Nightscapes are typically done using just your DSLR camera on a standard fixed photo tripod. The whole point here is to blend an interesting terrestrial foreground, maybe a cool-looking tree, a mountain range, a lake reflecting the sky with the celestial scene above. Capturing the Milky Way arching over a landscape is a classic example. Or maybe a dramatic moonrise behind a recognizable landmark. This type of astrophotography is often considered the most challenging, not necessarily technically, but artistically. Because success relies so heavily on finding a compelling composition, you have to find the right location, the right foreground, wait for the right time of night when the sky elements align. There's a huge art part involved in making a truly great nightscape. And actually, there's a variation of nightscape photography that does utilize the same kind of high frame count logic we've been talking about for deep sky. And that's creating star trails photographs. For classic star trails, you're usually back to using a fixed tripod. No tracking. But instead of one long exposure, which would overexpose the sky, you take hundreds and hundreds of consecutive short exposures, say 360 individual 30-second exposures, which adds up to 3 hours of total imaging time. Later, you use specialized stacking software, different from DSS, usually programs like StarStax or Sequator, that's designed to combine all those frames not by averaging, but by taking the brightest value for each pixel across the whole sequence. The result is those beautiful, smooth arcs of light showing the stars appearing to trail across the sky as the Earth rotates. You generally need at least 2 or 3 hours of total time to get really nice long arcs of 30 degrees or more, which look much more impressive than just short dashes.
Hashtag fact tags in a powder. Not true.
So to wrap things up, I think the key takeaway is that this astrophotography on the go approach, it's not just some, compromised second best option. It's a genuinely viable and actually quite powerful technique in its own right. You absolutely can produce final deep sky images that are remarkably comparable in quality to those taken using traditional single long exposure methods, even if you're stuck under heavily light-polluted city skies. The trick is to cleverly trade that long individual exposure time for a very high frame count, combined with meticulous calibration and sophisticated digital stacking. It really works.
Absolutely. And hopefully this deep dive has given you, the listener, the core knowledge nuggets you need to actually get started with this complex but incredibly rewarding hobby, maybe even tonight. You should now understand the counterintuitive power of stacking, how the signal-to-noise ratio improves by the square root of the number of frames, explaining why 100 short shots can equal the noise performance of fewer long shots. You know about the critical exposure time limit imposed by that pesky field rotation problem when using lightweight, portable alt-azimuth mounts, why 30 seconds is often the practical ceiling. And you definitely appreciate the absolute necessity of using proper 16-bit capable software for that crucial stretching phase to avoid creating ugly banding artifacts and actually preserve all that faint, hard-won deep space data you captured. But let's finish, as we often do, with maybe a slightly more provocative thought, something to mull over that brings us right back to that fundamental trade-off in astrophotography, the one that still kind of divides the hobbyists into different camps.
Right. We established earlier, pretty convincingly, I think, that two image stacks, both representing the exact same total integrated exposure time, say 75 minutes, will yield essentially the same final signal-to-noise ratio. It doesn't matter if it was 300 quick 15-second frames or just 3 long 25-minute forms. The noise level and the final result is statistically the same. That confirms our portable technique works perfectly well for noise mitigation. However, what stands out when you dig into why the dedicated, deep-pocketed imagers still haul out those incredibly heavy, precise, expensive German equatorial mounts to take those long 25-minute single subs, it comes down to the raw signal strength captured in each individual frame. In our example, the actual signal level, the sheer number of photons captured from the nebula in that single 25-minute exposure, was maybe 100 times higher than the signal captured in one short 15-second exposure. So while our short exposure stacking technique delivers equivalent noise reduction and produces fantastic, acceptable final images, especially from difficult locations, the traditional heavy, precise mount is still the king when it comes to achieving the absolute maximum possible signal strength and the highest initial contrast and detail within a single frame. And that quest, that drive for maximizing the raw signal captured, pushing the limits of faintness in a single go, maybe that represents the final frontier in deep space astrophotography. It's what keeps people investing in that heavier, more demanding gear. But for the rest of us, astrophotography on the go is here, and it's incredibly capable,